Welcome, thanks for joining section 11.4, limits at infinity. I'm going to do this all in one video, so the last part of it will be a little bit longer. Limits at infinity. So when we're talking about a limit at infinity, what we say is a function is said to have a limit at infinity, if the limit as x goes towards or approaches infinity of f of x is equal to L sub 1, or the limit as x approaches negative infinity of f of x is equal to L sub 2. This is basically just saying that the limits to infinity are how we find out whether or not we have a horizontal asymptote. You know, if I talk about some graph and I say as I move infinitely to the right, as I go infinitely towards x being positive and more positive and more positive, if it is capping out at some number, like in this case, y equals 0, then that is a horizontal asymptote. Most graphs, you don't have that. You know, if I talk about this function, the limit as I move infinitely to the right along this function, it's continuing to rise without bound towards infinity. So it's not equal to some finite number L. Now, we do note that they could be different. So whether or not we see it, the limit as x approaches infinity and the limit as x approaches negative infinity, you do not have to have the same asymptote on the right that you have on the left. Okay, so solving an infinite limit graphically. You know, if we talk about the limit as x goes to infinity, we are saying if we're starting on this function and moving infinitely, to the right, are we plateauing at some number that we're not going to cross? And as I continue this and continue this, what we can see is that this limit is not crossing 2. It's just constantly going towards and towards and towards 2. So that's the limit as I move towards positive infinity, because here's x getting larger and larger and larger and larger, but my y value is always going towards 2 as I go to infinity. Now the limit as x goes to negative infinity, so again I'm starting sort of along here, moving towards negative infinity. And what we're looking to see is, are we going towards some value as we go infinitely to the left? And as I go infinitely to the left, I would continue to get closer and closer and closer and closer to 2. So the limit in this case to positive infinity and to negative infinity is 2. And this is just telling me that there is a horizontal asymptote. At y equals 2. Because remember that your limit is a y value. So this is saying that we have a horizontal asymptote at y equals 2. So when we want to talk about evaluating these limits, which is what we're going to do in these 4 examples, we need to get an idea down. So when we're talking about going towards infinity, you know, when I talk about the limit as x goes towards infinity, what I'm talking about is 1 over infinity. Now, 1 over infinity, well, what is that? Well, the larger and larger and larger and larger that I make my denominator, the smaller and smaller and smaller and smaller this value is getting. So as this limit goes towards infinity, the value here would be 0. Now, if we talk about something like 1 over x squared, when I substitute infinity into this, I get 1 over infinity squared. Well, I mean, what's infinity squared? Well, that's just infinity. You know, it's just some larger infinity, but who cares? That's infinity. So again, 1 over infinity, I'm getting 0. So really, if I have 1 over x to the n, so if I have infinity being raised to any power, that's just going to give me 1 over infinity, which still gives me 0. Now, I want to talk separately about some other sort of interesting things. If I had the limit as x goes to negative infinity, we would have 1 over, I'm sorry, left out the whole function there, of 1 over x. So same thing as what we have here, but now going towards negative infinity. This gives us 1 over negative infinity. So when we're talking about negative infinity, we are making this number technically smaller, because it's being more negative. But if we just talk about the denominator and just talk about the infinity, that's getting larger and larger and larger and larger and larger and larger and larger. So the value of this fraction is getting smaller and smaller and smaller and smaller and smaller and smaller. So this is still 0, but we put a little minus up here. What this is saying is 0 from the bottom. And graphically, what this means is as I'm going to negative infinity, so as I'm going infinitely to the left, I'm going towards 0, but I'm doing that from coming from the bottom. Then, oh God, that was not the function I drew. The negative portion of my graph, since I had 1 over negative infinity. Over here, if I drew this one, as I'm going towards positive infinity, so as I'm going infinitely to the right, I'm going to 0. And because this would be a positive, I know I'm going to 0 from the top. So this is 0 from the top. So if we looked at another one, the limit as x goes to negative infinity of 1 over x squared. When I put negative infinity into this, I get 1 over negative infinity squared, which becomes 1 over positive infinity because that negative is getting squared. So that would give me 0, but now from the top. So 1 over infinity squared, I'm looking at something like this as I go towards negative infinity. I'm going towards negative infinity, which just means infinitely to the left. And I have a horizontal asymptote at 0, and I know that the function is above the y-axis because it has to be a positive number. So that's just sort of like an interesting tidbit. You'll see it again in calc, and that's a brief explanation of it. So let's get into these examples and see about how we do these. So earlier, way back when, you don't remember it because it's pre-calc and we forgot everything. Back in chapter like 2-ish, we covered rational functions. And in rational functions, we said you can determine the horizontal asymptote of a rational function based off of the degree on top and bottom. So in this case, we said the degree being equal on top and bottom. So here I have 1 and 1, means that a horizontal asymptote exists and it's equal to the ratio of the coefficients. So the horizontal asymptote is y equals 2/3. But what we learned in pre-calc back in chapter like 2-ish was a rule to sort of shortcut all of this. But we could actually prove that it's 2/3. You guys just sort of blindly accepted it. Nobody was like, why is that the case? So here what we're going to do is prove it. And we pretty much just have one strategy with these limits to infinity, and that is to multiply the entire numerator and denominator by 1 over whatever your highest degree is. So 1 over x and 1 over x. So this will become the limit as x approaches infinity of 2x over x plus 5 over x over 3x over x minus 2 over x. All I did was multiply that 1 over x into everything. So you could see here the x's cancel and the x's cancel. So this becomes the limit as x approaches infinity of 2 plus 5 over x, whoop, that's not an x, over 3 minus 2 over x. And if I now evaluate this at infinity, I get 2 plus 5 over infinity over 3 minus 2 over infinity. Well, what is 5 over infinity? In the last slide, we just talked about the fact that something like 1 over infinity is 0. And even though this is 5 times that, 5 times 0 is still 0. So this is really 2 plus 0 over 3 minus 0. So the limit here is 2/3. All right, looking at this next one, our pre-calculus rule was that if the degree on the bottom is larger than the degree on the top, then the asymptote is y equals 0. So I know that I should get 0 here. And that's helpful to me because I know what the answer is. It's 0. Now I just need to show all the work that gets me it. So I'm going to multiply on top and bottom by 1 over the highest power term, x squared. Neither of those squareds came out right. Nope, still no. Okay, well, that says squared. If I multiply that out now, I get the limit as x approaches infinity. Let's just make this a little bit smaller. Nope, that's a lot smaller. That's also a lot smaller. Of 4 over x squared. Okay, that apparently is not allowed. Okay, 4 over x squared minus, I can't, that's getting me too mad. Okay, minus x over x squared. And then we have x squared over x squared minus 2x over x squared plus 3 over x squared, which becomes the limit as x goes to infinity. And you can simplify these right away. That's totally fine. We have 4 over x squared minus 1 over x. So like you could go to this step right away. It's fine. And now we're going to evaluate this at infinity. So I get 4 over infinity squared minus 1 over infinity over 1 minus 2 over infinity plus 3 over infinity squared. Now, up here, we are going to sort of talk about something a little bit interesting here. When I have 4 over infinity squared minus 1 over infinity, what's important to realize is whether or not, both of these are 0, but it's important to realize what type of 0 you get as a result, because it's just sort of helpful. So I want to introduce it now. 4 over infinity squared. If I am squaring the denominator, what I'm doing to the value of this is making it smaller and smaller and smaller. If you talk about having 3 here, this would actually be 4/9 minus 1/3, if we were at 3. And then if we were at 4, I would have 4/16 minus 1/4. This is always larger because the denominator is smaller. So this is really 0 minus 0, but it's going to give me 0 from the bottom. And that's again because I'm subtracting a larger number. It's still it's still 0. It's just that I'm going towards 0 from negative numbers. So that's sort of interesting. Here it doesn't matter, 1 minus 0 plus 0. It doesn't matter which one of these zeros is larger because the 1 dominates the zeros anyways. So I get 0 from the left over 1, which is 0. From the bottom. 0 from the bottom. Which again just tells me I have an asymptote at 0, but I know what direction I'm coming from. I'm coming from below the y-axis. Okay, this next problem we're going to work out to the left. Probably should have told you to leave some room. I didn't, so deal with it. Looking at this, the degree on the top is 1. The degree on the bottom, if I were to multiply this out, and I'm going to multiply this out, is 2. So anyways, this is the limit as x approaches infinity of negative 3x plus 4 over 4x squared minus 16x plus 16. And that's just multiplying this out. Now again, I know I should get 0 as an answer because the degree on the bottom is larger, but I'm going to have to multiply by 1 over x squared in order to prove that I get 0. So this becomes the limit as x approaches infinity of negative 3 over x plus 4 over x squared over 4 minus 16 over x plus 16 over x squared. Now if I evaluate this at infinity, I get negative 3 over infinity plus 4 over infinity squared over 4 minus 16 over infinity plus 16 over infinity squared. Again, in the denominator, I have 4 minus 0 plus 0, because 16 over an infinitely large number is still 0. Up here, I still have 0 plus 0. But again, you want to be thinking about just which 0 of these is larger. I have negative 3 over infinity plus 4 over infinity squared. This term is smaller than this term because it has a larger denominator. So I'm taking a negative and adding a smaller number to that, which is still going to give me a negative. So this is 0 from the bottom again. So then the last example that we're going to look at, we said in honors pre-calc, just using our rules, if the denominator on top was larger than the degree on top was larger than the degree on bottom, then there was no horizontal asymptote. So what I am going to show here is that there is not any horizontal asymptote. I multiply by the 1 over x cubed and the 1 over x cubed. So this becomes the limit as x goes to infinity of 2 minus 4 over x squared. I don't like any of that, sorry. 4 over x squared plus 5 over x cubed over negative 3 over x plus 2 over x squared minus 5 over x cubed. Looking at this, if I evaluate it at infinity, I get 2 minus 4 over infinity squared plus 5 over infinity cubed over negative 3 over infinity plus 2 over infinity squared minus 5 over infinity cubed. Now, this is 2 minus 0 plus 0 over 0 plus 0 minus 0. So you can see here that you're getting 2 over 0, which is undefined. That means that the limit does not exist. You can still actually talk about that whole zeros thing. You know, here, 5 over infinity cubed, that's super, super small because my denominator is being cubed. Here, my denominator is being squared. So here's my dominant 0, and it's negative. You know, if you wanted, this one is a positive because it's 2 over infinity squared. This one would also be a negative. So this one, still being my dominant one, would give me 2 over 0 from the bottom, which means that this has a vertical asymptote. I'm sorry, not a vertical asymptote. I'm thinking regular limits, not limits to infinity. This doesn't have a vertical asymptote, but its end behavior, this is telling me that it's going towards negative infinity. So the limit doesn't exist. What this graph is doing is just falling on the right side. So it's going downward towards negative infinity overall. And if you want, just put that into your calculator. Hopefully you'll see that, unless I just did something a little bit wrong here. But what you should see is that as I go infinitely to the right along my function, this is just decreasing infinitely. Okay, that was super fun. If you don't get the whole like 0 from the top, 0 from the bottom, don't worry about that. Just be able to get these limits like 0, 2/3, 0. Limit does not exist. Get that, and then, you know, if you want to extend on that a little bit, be able to think about, you know, where is this actually coming from? 0 from the bottom. This is going towards negative infinity. This is more calculus bound. Okay, have fun. Thank you.